Hello everyone, Namaste. I am Ramnath who would like to share with you some information on the VLSI topic, why EM in SOC design, an issue to be solved. This is part 2 and the previous part can be obtained from the YouTube with the same title. The next part will be provided in the coming days. Please feel free to provide your comments or any suggestions. Thank you. Yeah, in part 1, we have analyzed how EM occurs in a conductor and also in day-to-day life, how water flows and how the current becomes more turbulent and it takes away the soil also during floods and other events. So, even in the same way, even a conductor also, when the electron flow becomes more turbulence, it will also move the atoms towards the anode. That one we have studied, understood. In this part 2, we will figure out some more details on the EM. So EM, as you know, it occurs in any conductor where the current density limit is higher than the limit it can withstand. So you will observe that in a SOC design there are multiple places. I mean, it can occur in a signal EM, that means like in the signal lines or in the power lines. Okay, we will learn more about it further. So in this SOC design, if you observe, that means like in this small portion there is some logic here, as we have observed in the earlier part also. Like we will figure out like now how the current density in a specific location will make a difference, and we will study that in more detail. This is the conductor which we are talking, and this is we will study further the behavior of EM. Yeah, if you observe here the gate, this can be a buffer or inverter or a NAND gate, for that matter anything, any other gate. So this conductor, if you see its representation here, you will analyze that this is the width part, this is the length, and this is the thickness. Current is moving from one buffer or one gate to another gate, so it is moving in this direction. So length is shown here. So if you look into further like how EM comes into play, you will understand that when the current is going in this direction, this part, that means like this is the area. Okay, so with W and thickness, with that how much is the density going, that is how we should calculate. So when you figure out how much is the current density going and what is allowed for this metallic conductor, then if that current density going through this current at that point of time, if it crosses the current density limit of that conductor, then the electromigration will take place. So in general, for this specific metal conductor, thickness of this metal is constant, because the whole SOC design is made with say if you consider about one layer, say metal 4 in this case, then this thickness of that metal 4 throughout the SOC design is constant. So to figure out what is the current density of this metal 4, that means like the current divided by the area, that is W by thickness. So you will figure out that current by width. So this since the thickness is constant, current density is controlled by the width and the current only. Okay, so definitely in a SOC design you can have the same metal 4 conductor drawn with different dimensions. Okay, so in general in SOC design you will draw with single width or double width or triple width. Okay, So but in analog design, generally you will draw with the same metal 4 with the multiple widths. Okay, it doesn't need to be sticking with specific integer amount of widths. So if you observe in the technology here, I am showing only the one specific technology where the number of layers are M1 to M6. So but in the lower geometry nodes, the number of metal lines can be many. So here this is the metal 1 and this is the metal 2 and this is metal 3. So this is metal 4, metal 5 and metal 6. You will observe that in this, since we are talking about the soft design, digital design, so metal 1, metal 3, metal 5 are in vertical direction, or in this way you can consider them as horizontal, and in this way you can consider as vertical. So you can consider that metal 2, metal 4, metal 6 are in another direction. Okay, so if you take this one, you also observe that metal 1, metal 2, metal 3, metal 4 are somewhat in the same thickness. More or less metal 4 is slightly higher, and if you observe, definitely the metal 6 is having a larger thickness, and this depends upon from one technology to another. In this may be in CMOS 140, or sometimes if it is go to CMOS 40, or if you go to CMOS 60 nanometer, these number of layers will change and their thicknesses also will change. Even the width also will change. So if you take the resistance of a specific metal conductor, so assume that in this specific one, how the metallic resistor depends is, simply speaking, it is R equal to rho L by A. So here L and by A means T into W. Okay, this one, this is the W and the thickness. So that phase leading to. So that is the resistance by square area. And since the thickness of the metal offers higher thick metal offers low resistance, so it is usually EM should be better for higher thick metallic layer. And coming to that parallel capacitance, so parallel capacitance is dependent upon the epsilon A by D, but here we are talking about per unit length. So instead of say, actually you should be thinking about this area for the parallel capacitance. Assume that there is one more layer beneath. So what is the parallel capacitance between this layer and one below in the same fashion? Okay, it can have more, but we will take the overlap capacitance. So that area will be W into L. But since we are talking about parallel capacitance per unit length, so that will be A epsilon. A is, instead of A, we will just put W because we are talking about unit length. So epsilon W by thickness. So higher thick metal layer, even here also offers lower capacitance. So if you observe, that is why if you observe in a higher routing, higher thick metal layer, it is better we use it for critical wire routing. Even in the clock routing or some special signals which need to be routed with lesser delay, we can use the thick metals. Or even for power routing, for reducing the IR drop, the higher top metal layers can be used. So for example, if you observe the TECLEF, which is used in physical design and in other soft design flows, you will I have just taken a numerical part of it. So there are different attributes for metal layer. So for example, resistance R per square, or capacitance, the parallel capacitance per distance, and for there are also EM related values. So these are all for AC current related, average, RMS and peak. So these are all AC current density, and there is also one more for DC current density, which is for average. So this is for metal 1 layer, this is for different widths of metal 1, and here it is for layer 2, this is for different widths of metal 2, and here it is layer 6, this is for different widths. So if you observe, naturally the metal 6, it is having the higher width. Okay, so compared to metal 1, metal 2, this is having the higher metal width. If you observe the average RMS and peak values, you will observe that going to higher width, definitely it is larger, but comparing to metal 1 to metal 6, these values are way higher. So that means like AC current density limit is larger for the metal 6 because it has higher thickness. Because if you observe the resistances also, it is way lesser compared to this one. Even parallel plate capacitance also is way lesser. And you will also observe that in our day-to-day life also, this is a mobile phone and a laptop. If you see the power charging cable, this thickness and this thickness is completely different. Okay, this is definitely a way lot thicker than this cable. The reason being, the current needed for this device is smaller than this one. So definitely you need a larger cable, that means like a thicker cable than this one. Yeah, over the years, the metal width is shrinking. Because of this, current density is actually rising. So you will observe that there will be certain EM violations are more seen in the later part of the years rather than in the earlier period. Okay, so these are hillocks and voids are formed during this one. So if you get into this breakage happens further, it will become a void, a open, and here some hillocks have formed here. So like that. So this is higher. This will lead to a reliability issue. So that is why EM effects can be seen in the failure of the devices. So EM affects the reliability of the interconnect, thus lowering the mean time to failure of the system. So it is better we figure out earlier these violations, and we will also make the soft design interconnects robust enough that EM violations are not seen in the operating conditions. Yeah, these EM issues we should avoid it in the soft design, and it should be possible in two phases. One is during the design phase, we can avoid and prevent them, and in the once you have some silicon, you can again figure out whether there are any EM issues in the design, and you can weed them out, take them out to improve the yield at the customer end. So there are so many failures in the silicon due to several reasons, and we will here talk about electromigration. Okay, so electromigration can lead, as we have mentioned, due to voids or hillocks, either opens or shorts. This is mainly will occur in the interconnects. This interconnect can be a gate-to-gate interconnect or power signal line. So the main reason of this is like we wanted to improve the number of dies, good dies in the wafer. If we don't catch it within the before the system is made, we will lose a lot of money. Okay, it is better we figure out at the early stage. So to figure out where the problems are occurring, we will use the fault logic method, wherein we will abstract out this EM problem, and we will, this is a physical defect, EM is a physical defect, and we will abstract it out the fault model and then come out with different ways of addressing the and detecting the fault. So one can be a stuck method where we will point the net to be stuck at 1 or stuck at 0. Actually speaking, there is no net connected to logic 1 or logic 0 because of the physical defects in the silicon. The logic will be associated net will be appearing like it is stuck at 1 or stuck at 0. So in the same way, transition fault. So we will let us analyze this specific logic wherein we wanted to figure out what is the test pattern which we need to apply so that the N2 node can be stuck at 1. So to figure out that one, we will set these bits at the inputs of this logic, and we will figure out whether, and we will ensure that 0 will be seen at the N2, which is the desired one, and we will figure out whether it is stuck at 1 or not. If it is not stuck at 1, then 0 will be seen and the final output will be 0. But if it had been stuck at 1, then even though we are propagating 0, it will be seen as 1 only. So the final output will be 1. So this is the way to figure out the specific test patterns and figuring out the node. In the same way, to figure out the test pattern for detecting a rise transition at N2, then we need this kind of two patterns. Okay, 1, 1, 0. Later on, we should apply 1, 1, 1. So then these two patterns will be seen. So N2 will go from 0 to 1, N3 will remain at 0. So because of this, when the pattern changes from 0 to 1, you will figure out whether there is any problem with the rise transition. So that is how we can figure out different defects. So that means like why we are figuring out this is because of the electromigration, this interconnect metal layer may not be working as expected. So this resistance might have increased. That means like the void will be formed not fully that it became open, and but it has become somewhat degraded. So because of that, the resistance of this conductor is increased, because assume that in this specific case the electrons have to move within this small distance. Okay, so small width, I mean. So because of this, resistance has increased. So because of that, the rise transition will change. So the rise delay will also change. So that should not happen. That we have to figure out in the silicon chip, and then we have to take those offending chips. That is how we will improve the yield of the wafer. So just wanted to mention like the first DFT paper was published in 1959, 6 years before Jack Kilby and Robert invented the integrated IC.